voice. It's very bizarre. Oop, okay, a few more people coming in now. Oh, and Q&A. Okay, John, he's in Toowoomba with a, oh gosh, you get around, John. A microphone and a crap connection. Okay, we might just leave that for now if you're happy with that. I'm just very puzzled by the fact that usually I'm able to, it is on, yeah, the URL is on, it's not on the front page, but it's in the online learning calendar for this event. Welcome to those who have just joined us. Welcome to this instalment of Technorama Tuesdays. We'll just wait a little while until a few more people join us. What I might do is I'll start the poll because I just want to get a feel how do. I wanted to launch a poll, but it doesn't seem to be allowing me to, but I will. There we go. You should see something pop up. Oh, Jason's outstanding. I'm going to like that. Is the chat box popping up for you, Mike?
Yeah, I saw it popping up there.
Oh, beautiful. Okay. Hi, Buzzer. Welcome to this evening's webinar. Scott and Colin, welcome. I thought I was being very clever with organising this poll, but the Zoom has since removed the option for me to share it with you. Unless it, no, it's not that. It's very annoying. Okay, we will just wait a couple more minutes for a few more people to get here. I might just amuse myself by seeing if I can find the poll that I'd organised, and we'll get started with this evening's webinar on the 2 ohms in just a couple of minutes.
Better make it quick, Barry.
You know what I might do while we are all here, I'll just show everybody where they can find details of the upcoming webinars. It's on the Technorama website, but on details of this webinar and the other webinars that are run in the community broadcasting sector. We have it on the CMTO website. And if you go to find a course, just move my screens. Oh, it's not, I can see it's not working for you. If you go to find a course, we have the online learning and webinar little tab. And here you will find each of the webinars and conferences that happen in the sector, and other important meetings that are relevant to the wide majority of us. You'll also find a bank of the recordings of the Technorama Tuesdays webinar series, as well as the CMTO, the CPAA webinar series, which is also supported by the CMTO. So you'll be able to find that just there. But if you click into any of these events, you will find the URL to each webinar. So unfortunately, that's not a hyperlink, but all you have to do is just copy that and you'll be able to join the webinar. We do have them available well into the future. So if you want to get organised you are more than welcome to register right now for those. Okay. Welcome to those who have just joined us. Welcome to Hannah from the CMTO office. Lovely to have you. And also Elaine from all the way over in WA. Thank you very much for joining us this evening. We will start this evening's webinar. Are you ready to start, Mike?
I am. Let's go with it.
Beautiful. Do you have a video? Do you have a webcam available to you, Mike?
Do I have what? Do I? Whereabouts is it? Start video. There we are.
Yeah, start video. You should have it there.
Yep.
Beautiful. Wonderful.
There we are.
There you go. Okay. Thank you, everyone, for joining us for this evening's webinar on the two Ohms. This is one of many in the Technorama Tuesdays webinar series, and this one's aimed at those of us like myself who are not so technical, and it's a bit of a basic introduction to electricity. And I think the way that we are going to play this is Mike is the expert, and we will have a few other experts in the room, such as Technorama President John Maisels, and I am far from being the expert, so I'll be interjecting at points to clarify and really refine my understanding of this important topic and understand why it's important to us all. So I just want to point you all to the Technorama website, because it's there you can join up to their e-news and find all the information that you need to know on the upcoming events like Technorama Tuesdays and any other important information from Technorama HQ. So I encourage you to do that if you're not already a subscriber. This is a little bit of electricity humour that I found on the internet. I hope it gives you a bit of a laugh. It definitely gave me a laugh when I found it, and I sent it to my father, who is an electrical engineer. So I really should know a lot more about this. But Mike, would you maybe be able to explain the humour in this? I think I like it because it's monks, but maybe I don't get it.
Well, I think the monks are known for wandering around saying, sort of humming, saying, and somebody's just put the OH in front of it and said ohm, which is the unit of resistance, which is part and parcel of the understanding of electricity.
There we go. Beautiful. We've got our education underway. I thought that was quite a funny one. So what we're going to be talking about during this webinar is what Ohm's Law has to do with volts, amps, resistance and power, and tools that we have at our disposal in our stations to measure this, and really why is it of relevance to technical and non-technical members of a station. So we'll be running through the basics with the assistance of Mike, and once again a little bit more humour. And I do get the meditation component of this joke, but what Mike is the I suppose technical humour underneath this. Do resistors don't like to ohm, or don't?
I couldn't figure that one out myself. I just couldn't see the connection. but there again, I'm not into meditation, so maybe I'm too technical to understand it. Maybe other people might find it easier.
Maybe that's it. 10 points to anyone who can figure that out in the chat box. Give it a whirl. Okay, so the first part of this presentation, and this is put together by Mike, thank you for that, is a kind of breakdown of where we're coming from with this. So the universe is made up of, and why it's relevant, the universe is made up of matter. All matter is made up of atoms. Atoms consist of charged particles called protons, neutrons, and electrons. And protons have a positive charge, electrons have a negative charge. Well, neutrons are not charged, so they're the neutral, the middle ground. And if these charged particles it's these charge particles that give rise to electricity as we understand it and apply it in today's electronic applications. So as far as I already understand it, these are the 3 core components of an electrical current. Is that right, Mike?
That's correct. That's correct, yes.
Okay, good. Oh, what would happen, and this might be a very silly question, but I'm here to ask the silly questions. What would happen if one of those elements wasn't present?
I guess from the point of view of lightning and static electricity, you can say that you don't have a current flow, you have a static charge, and you have a current flow in a bolt of lightning, but before that, when you've got the charges built up in the clouds and people's hair stand on end, that's when the current's not there. Resistance can be like an insulator, and it's effectively not allowing any current to flow. And voltage, if the battery's flat and there's no volts coming out of it.
Oh, okay. Fantastic, which I hope never happens in any of our stations, but we will discover how we can prevent that from happening. So I'm going to pop the steering wheel over to you, Mike, and I'll just make you a host so you can share your wonderful presentation with us. Just give me 1 sec.
And I'll go and find my presentation. Where is it?
Yeah.
Down the back here somewhere.
That will be useful. Yeah.
Okay, slideshow from the current slide, and right, electricity.
Okay, I'll just can't see it just yet. It might just be taking a minute to come up. Because you are a host. And it just worked for us, didn't it? Which would be mental if it doesn't. This Zoom, I think it's really fantastic, but it really does not enjoy me using it. Sorry about this, folks. It'd be pretty useless without the presentation. And there's nothing that's popped up on your screen, Mike, that said share presentation. You might have to press share, actually.
Share.
Down the bottom.
Let me just go end show. Oh, right, okay. When I bring that up. Down the bottom here.
Yep.
Share, right. Okay, go to that.
There we go. I think that's...
Somebody got it?
There we go. We got it. We're all good. Good stuff.
Okay, slideshow from the current slide.
Yep, there you go. Good stuff.
Okay. Electricity. If a substance allows electrons to move through it easily, it's called a conductor. Conductors that you'd be familiar with would be tin, gold, lead, iron, steel, all the metals. If it does not allow a passage of electrons, it's an insulator. Insulators being ceramics, glass, even timbers, depending on whether they're wet or not. So things that you would use as an insulator. The flow of electrons along conductors equal to the charges is an electrical current. Electric current is a flow of electrons through a conductor like copper wire, and this can be compared to the flow of water through a pipe as a result of the pressure generated by a reservoir. That pressure is like the voltage generated by a battery, which drives the electrons through the circuit. So we have here a large pipe, large amount of electrons flowing in a bit of copper wire, a narrow pipe, and lower current flowing. Electric current is the order of flow of electrons along a conductor. Because the electrons are the particles that can move, the flow will be from negative to positive. Electric current is represented by in formula and current symbols by the symbol I. Current is measured in a term called amperes, and it's abbreviated to A. For a current to flow, there must be a difference in potential between 2 points. The difference in charge is known as voltage, potential difference, or electromotive force. Those three things mean the same. Voltage uses the symbol V or E, and that's V taking it from voltage or E from electromotive force. And voltage is measured in volts. Going back to our analogy of water and voltage, water voltage, now the higher the water is stored, the greater the pressure at the tap below. You can imagine a reservoir that's way up in the mountains and there's a lot of difference between it and somebody's tap. There's a fair amount of force there. But if it's only in somebody's tank in the backyard, then there's not very much difference in height between the tank and the tap. There's very little pressure there. For a current to flow, there must be a conductor connecting 2 points to a different voltage. Whenever we have movement, there is an opposing force. The opposition to current flow is called resistance. Get back to our little fella with the monks all sing there saying Om at the beginning of the show. Resistance uses the symbol R for the formula. And resistance is measured in ohms. Before we have a look at some practical electronic circuit and do a couple of Ohms Law examples, let's pause for a moment or two and see that we understand what we have looked at so far. Do we have any questions?
And if anyone has any questions, either use the Q&A box or the chat box. Can you, just going back, Mike, to your water analogy, can you recap for me on the three, I've already forgotten, the resistance, what are the three components of that analogy, the electrical components?
Okay, in electricity we have voltage,
yeah,
which is the pressure, we have current, which is the flow of electrons, and we have resistance to that flow. If we compare them to water, the voltage is the actual amount of water that's in the dam that's going to push the water through the pipes. The flow of the water through the pipes is the equivalent to electrical current, and the resistance is how much opposition the wire offers to the current flowing, or in the case of the water analogy, how big or small the diameter of the pipe is and how much water can actually pass through the pipe.
Oh, okay. Okay. And there doesn't seem to be any questions in the chat box or further additions to that, so I think we can continue.
Okay. In a circuit, the voltage, the pressure, and the current and the resistance are related. This relationship is called Ohm's Law and states that I, the current, is equal to the voltage divided by the resistance, or another way of putting it, the current in the circuit is directly proportional to the voltage and inversely proportional to the resistance. Or if we write it down as a formula, I equals V over R, or V equals I times R, or R equals V on I. That's just straight out mathematics for the transposition of that formula. Power is the ability of force to do work. In electrics, this can be turning a motor, causing a light bulb to glow, or causing an electromagnetic wave to form around an antenna. Electric power uses the abbreviation P for the formula. Electrical power is measured in watts. Electrical power depends upon the voltage and current in the circuit. As a formula, P equals V times I, or V equals P over I, or I equals P over V. You'd all be familiar with your transmitters and what power they're putting out. It might be 1,000 watt, it might be a 250 watt. That's exactly the same power that they're talking about as what you have in the rating on your transmitter at your station. And once again, we come to this little triangular box, and we can see that V equals P over I. You note the use of the Ohm's law and the power triangle to explain the relationship between volts, amps, and resistance and power. The concept is that covering the element that you need to calculate, the other two elements are shown in the correct relationship. So if we come to this one, and I want to find out I, and I cover that over, then I will equal V over R. If I want to find out what V is, and I cover that, it's I times R. So no matter which way around you want the formula to work, we're covering up the one you want to find. The other two will be in the right relationship to show you how to calculate them. DC current flows in one direction only. A battery provides a source of DC. Provided there's a circuit, current will flow from the negative to the positive. Many simple devices, such as light bulbs, will operate on DC regardless of which way the current is flowing. The direction of current flow is known as the polarity of the circuit. I don't know if any of you remember back to some of the very early motor cars that we had here in Australia just after the Second World War. Actually had positive connected to Earth and the negative polarity to drive all of the car off, because nowadays just about everything, all of the current cars are negative Earth with a positive polarity to drive everything. More complex electronic More complex electronic devices and or circuits can be damaged if connected with incorrect polarity. Excessive voltage can also damage electronic components. There are many ways to prevent damage to electric equipment from connecting of the power source incorrectly. However, most suffer from some form of degrading of the performance. It's wise to Google that particular statement in Google and have a look for yourself to satisfy which methods are the right ones to suit your particular applications. Just a quick little note there about alternating current. The power that's distributed around the houses and streets is alternating current. We'll look at alternating current more in a later presentation. Okay. How are we going? Any questions out there at all?
Not as yet. But I'll encourage anyone to include any questions or comments that you may have. No question is too silly. I've probably got a few up already. Jason says, all good. So I think you're explaining it pretty well. And I look forward to having a couple more station-specific examples.
Right, okay. At any time, if you've got a problem there and want to ask a question, just flick it into the chat box and Emma will pull me up and we'll have an attempt to answer it.
Yeah.
Okay. So in a circuit, we need a battery for a source of power, and it's a symbol for a battery. A LED lamp to demonstrate the use of power. We're going to draw up a circuit with all of these in it shortly. A switch to control the flow of current, and a resistor to limit the current to a safe value. Battery is a standard device for electronic equipment with an output voltage of terminals of 9 volts. Not all have got 9 volts, but in this particular case, we're taking a battery with 9 volts output. The symbol used for an electronic circuit is this little fella here, a couple of cells connected together. The voltage is important for use in the Ohms Law formula. This voltage here that we're talking about, 9 volts. The LED lamp to demonstrate the use of power. The symbol used in electronic circuits is this little fella here, a diode with a ray of light coming out of it. A typical red LED will require about 2.2 volts to light it up, and it will take about 10 milliamps for full illumination. These details are important for use with the Ohms Law formula. The switch will allow current to flow or not flow in the circuit, just simply to turn the light on or off. It's generally practiced to put the switch in the positive lead of the circuit, and the symbol used in electronic circuits for the switch is this little fella here. And the resistor to limit the current to a safe value. We know that the LED, from what we said before, takes about 10 milliamps to glow to full brightness, so we don't want the current to be any higher than that. There are other symbols for resistors, but this is the one that I use most of the time. And Ohms Law to calculate the value of resistance required to limit the current to 10 milliamps with a potential across the LED of 2.2 volts. Everybody keeping up with me?
Yes, I believe so. Hannah's asking, she said, you're probably getting to this, but what's the benefit of AC compared to DC?
In terms of the losses that are generated in the transmission of power, you'll see those really big power towers that go across the countryside from places like Yallourn, where the power is generated down to the cities. If you ran that power at DC, the losses in the lines would be so much that you wouldn't get hardly anything out of what you put in at the generating end at the far end of the city. AC is a lot less lossy in transmission, and it's a more efficient way of doing it. There are other examples, but that's probably the biggest one of the lot.
Okay. What would be, is there an example within a station that would be relevant?
Well, you deliver AC into the station from the mains. The power that comes in off the street is AC.
Oh, okay. Yeah.
So you're dealing with, that's what they give you to work with.
Yeah. And Elaine's actually contributed to the conversation and just said that it took for years for Broome to get onto AC.
Yeah. A lot of the country stations are in really remote areas would be generating their own power or having solar panels and charging batteries and various alternate ways to getting the power they need other than being connected to the grid.
Yeah. Okay, cool. Thanks.
And now, of course, a lot of people are trying to go off the grid and prove that, they can be totally independent of it. And quite a few people going down that path too. So,
does that have a negative effect on the global structure of the grids?
Only in the profit that the power companies make.
Oh, okay. That's good. Good to know. There's no more questions at this point.
Okay. Before we put the circuit together, we should look at a piece of test equipment that will allow us to measure current, voltage, and resistance. This instrument is known as a multimeter. A nice yellow-looking device here. Essentially 3 meters in one package. A voltmeter to measure voltage, a current measure to measure amps, and an ohm meter to measure resistance. Within each of these meters are several switchable ranges. What I mean by that is that if you're wanting to measure a car battery, it's 12 volts. You can switch it to a 20-volt range. But if you wanted to measure the mains voltage from the power point, which is 240 volts, you would need to have another range. You could switch it to a 600-volt range, for instance, so you can measure 240 volts. So that's what I mean by switchable ranges. And able to read very small or rather large measurements. 2 leads are provided for connection to components or circuits, a black common lead and a red active lead. Later on this evening, we'll use a multimeter to verify the results of our Ohms Law calculations. Let's gather some data about the components in our circuit. We said before the battery is 9 volts. It's rated at 500 milliamp hour capacity, which means it's half an amp, 500 milliamps being a half of an amp. And that means that the battery will be able to deliver a half an amp for 1 hour. That's why they call it milliamp hour capacity. Switch is rated at 1 amp. Normally open contacts. It's general practice to put a switch in the positive lead of the circuit. And the lead is a 5mm red, rated at 2.2 volts, drawing 10 milliamps of current. The components we have not spoken about is a resistor. And this is where we have to apply Ohm's law to find out the value in ohms so that we limit the voltage applied to and the current through the lead. Let's apply a little maths. The battery is rated at 9 volts, but we only need 2.2 volts for the lead. Therefore, we need to remove 9 minus 6.8 volts with a resistor. Also, we need to limit the current to the lead to about 10 milliamps. Still going okay?
Yes, all is going well. No questions thus far.
Okay, let's draw up the circuit on a bit of paper. The battery is simply designated as B1, and we use that symbol there. The switch is labelled SW1, and we said we use that one. The lead is there, and the resistor. If you have more than one resistor in a circuit, it would be called R1, R2, R3, etc. The same thing with switches and batteries and everything will be the same. When the circuit is drawn, interconnecting wires are simply lines on a bit of paper. So here we've got this bit of wire connecting the battery to the switch. It's just drawn as a line on a bit of paper. The switch to the lead, etc. The switch is operated and current flows in the circuit. By using the data we collected earlier, we can calculate the current flowing in the circuit and the value of the resistor. We know from our formula that we did before that R equals V over I. And we know that I is 1/10 of an amp. And we know that the voltage across the resistor is going to be 6.8 volts. The 2.2 that we need to drive the lead, taken away from 9 volts of the battery, gives us 6.8. So therefore, when we put that into Ohm's law, R equals 6.8 divided by 0.01, or 680 ohms. The only thing that we need to be concerned about in the circuit is the polarity of the lead, and the cathode must always be connected to the negative side of the battery, or the anode to the positive side of the battery. If you don't do that, it won't work. Most resistors are produced in a range from 1/4 of a watt to about 5 or 10 watts, and therefore we should use a power formula to calculate the power rating required. We know from our Ohm's law looked at before, P equals V times I. V is 6.8, the same voltage that we got from before, and the current is 0.01, so it comes out to 0.068 of a watt. It's considerably less than 1/4 watt, so a 1/4 watt resistor will be fine in the circuit. So this is what we end up with eventually with our circuit. We've redrawn it. We've got the switch closed, the current's flowing, the lead's there. It's got 2.2 volts across it, at 10 milliamps. The resistor is 680 ohms, which is a standard value, at 1/4 of a watt. And the whole light's working, and the lead's got a bit of bright light coming out of it, red light. So now we're going to have a look at a little video that's telling you how to use a multimeter.
Here is a variety of instruments we can use to measure.
Sit back and enjoy.
We need to be able to measure electrical quantities from tiny values like microamps through to large values, maybe hundreds of volts. We can replace all of these instruments with just this one device, a multimeter. It lets us measure both voltage and current over a wide range of values. It's called a multimeter because it combines many instruments in one. We can also use it to measure resistance and AC voltage, amongst other things. Now, to use it to measure voltage, I'm first going to plug in the leads. Black lead always goes in the black socket marked common. To measure voltage, I'll plug the red lead in here where it's marked V. To measure an unknown voltage, I always start off on the large range. This range here says 600 volts. That's the full scale deflection. That means the largest voltage that the instrument will read on this range. Let's plug it in to this battery. You can see I get a reading, but only to one significant figure. How can I be more precise? I move down to the next range lower, marked 200 volts full scale deflection. You can see that my reading is now 1.5 volts. That's two significant figures. I can be more precise by moving to the next lower range. This range is 20 volts full scale deflection. My reading is now 1.54 volts. The next range down is marked 2000 M. That means that the full scale deflection is 2000 millivolts, or 2 volts. The reading is now 1535 millivolts. The next range down is marked 200 millivolts. If I was to change down to this range, you can see that the reading is too high for it. Let's do it and see what happens. The reading has now gone, and I just get a 1 on the display. This means that the voltage input is too high for that range. If this happens when you're doing an experiment, you simply need to increase the range until you get a proper reading.
How did that go then? Did everybody understand it?
There's no commentary in the chat box, but I think it was pretty straightforward. Oh, yep. We've got a yep from Hannah. I'm still a bit puzzled, but I think that we've still got a bit of webinar to go to sort that out.
All right. That was talking about measuring voltage. There's a different way that you have to configure the instruments when you want to measure current. We've got another little video here which explains how to measure current. A little bit of audio there to wake everyone up.
Back. In this video, we're going to show how to use Centec digital multimeter to measure current in a simple circuit. And it's very different than measuring voltage. If you watched the previous video on voltage measurement, we're going to use this meter in a very different way. So first, we're going to show how to set up the meter and how to connect the meter to the circuit. And then the last thing is the schematic symbol for this. So first of all, this dial knob has many settings, and we're going to look for the one that says DC amps, direct current amperage, current really. And we're going to set it to the 10 amp scale, because we know that the battery over here is not going to supply more than 10 amps to this little circuit. Now, the probe leads have to be connected very differently for this measurement than we saw in the voltage measurement. First of all, the red lead has to be plugged into the socket that says 10 ADC, 10 amps direct current. So if we don't do that, we won't get a measurement. So we have to move the plug to the one that's indicated by that. You can see that they're kind of connected by these little arrows. And now our meter is configured correctly to measure current. Now, can I just take this and measure current by poking the positive and negative terminals like that? Not so much. Probably what will happen if I do that is it's a high likelihood that I'll actually blow the fuse and damage this meter. And if you do that, then you will have to buy me a new fuse and install it, or you'll have to buy me a new meter. So don't take the probes in the ammeter setting and put it directly at the battery. Now, when I say ammeter, that's a meter that's measuring amps or current. So what we have to do is to break the circuit. You actually have to turn this, disconnect somewhere, cause a break in the circuit. And then the current has to flow through the meter. So it's going to come out of the red lead, through this red lead, through the meter, pass through the meter, and the meter is going to measure the current flowing through it, back out its negative lead, the black lead, and then the black lead over here is going to pass the current through the rest of the circuit. So basically, we have to bridge the gap in the circuit using the meter. So as you can see, the light bulb's off, but if I touch the meter leads to here, I get a current reading of 0.15 amps, and the light bulb turns on. If I break the circuit by moving the probe lead off, no current. And again, if I have the leads going this way, if I put the black lead on the more positive end and the red lead on the more negative, the circuit works, but I get a negative reading on the current. So that just kind of tells you which way the current is flowing. So the important lesson is that to measure current with an ammeter, you have to put the meter as part of the circuit itself. It has to become part of the circuit. So the schematic symbol for this is battery, resistor. We're going to put an ammeter, A for ammeter, in a line with the resistor, the bulb, and the rest of the circuit. So the ammeter, which is the digital multimeter set to amps, becomes part of the circuit. So this is the red wire on the meter here, and this is the black wire. And current is going to flow through the ammeter, through the resistor, light up the bulb, and come back. If you don't do that, then you won't measure the current correctly, and if you touch it directly to the battery, you will have to replace the fuse on that or buy another meter.
Now it's time for a short quiz. True or false? You can damage the meter if you connect it directly to the battery terminals. That's true. If you do it, you'll buy us a new meter. Which schematic shows the ammeter correctly measuring current through the resistor? Look closely at the 4 diagrams. The answer is A. The ammeter is in series with the resistor.
Okay. The only thing that we didn't discuss with the multimeter was what way around you connect it to measure resistance. And if you've got a resistor sitting there as an individual device, and you've got the 2 probes, and they're connected as if you were going to measure voltage between the common and the DC voltage connection, then simply put it across the resistor. You don't need to power up the resistor in a circuit at all, because the multimeter has got its own internal battery that will push current through the resistor, and it will come up and show us a value in ohms on the scale. Okay. That's about it. What do you want to throw anything into the circle and see if we can help with it, or?
Yeah, sure. So Hannah's just asked why, and I think this was a few slides back, why is the resistor put at the end of the loop and not before the LED?
It could go anywhere. It's a series circuit. We've got the switch, the LED, and the resistor, and they can be in any order once it's a series circuit. If it's a combination of series and parallel circuit, like they showed with some of the connections there with when they were asking you which was the correct way to measure the current, then it may be important. But in that simple little circuit, because the current's flowing through all of the components, it doesn't matter where the components are in the circuit.
Oh, okay. Thank you. And she's asked, how do you measure things in parallel?
By things, does she mean resistors or?
Hannah, I'll just get you to pop a clarification in the chat box or the Q&A box. Does anyone else have any questions while we're at it? We've not got long of this webinar left, so I'll just throw it open to you all. Is there anything else you'd like to add, Mike?
No, I don't think so. I think it was good that everybody seemed to be following it. And of course, this is recorded, so if you want to sit down and have another look through it at some other time and maybe absorb it a little bit stop-startish, so that's quite okay.
Yeah, that probably would be handy. I'll just throw to John, who is our Technorama board president, and see if he had anything else he would like to add. We did have an issue with trying to get his microphone working, but maybe even in the chat box. But, perhaps not. Okay, so Hannah's come back with a clarification to that question, Mike. She's asked, so you measure batteries in parallel, but what if you have things running in parallel sequence? How do you test different components in a parallel series?
You would have to disconnect each component and measure it as an individual component, and then you wouldn't have any interaction between it and the other components that were in parallel with it. Like we had two resistors in parallel and you wanted to find out if they were both the values they should be, you could do it by calculating the formulas for it, or you could simply just disconnect one end of both of the resistors and measure them with a meter and see that they were both what the colour coding on them said they should be.
Okay, great question, Hannah. Thank you. Elaine says, thanks, Mike, and that she will go through it all again. So very good information. And
I hope that next time the technologist asks you to measure something on the station, because he's a couple of 100 kilometres away somewhere else, you'll be able to pick up the multimeter and switch it to the right range and measure something and get on the phone and tell him this is what it is, and he'll be quite startled to think that you actually know what you're doing and how to read it.
And I will just ask quickly, what is an emergency situation, perhaps, in the context that you've just outlined, if the tech's not available, that you can think of that this information would be applicable?
Well, just exactly what I said. Say the tech was suspicious that the batteries had gone flat on the station when you were running off the batteries, but he wasn't sure. He might ask somebody to get a multimeter and measure the voltage of the batteries, and say it's supposed to be a 12-volt battery, and you come back and you say, oh, it's only reading 8 volts, because you know how to use the multimeter now, you know how to read what's on the screen. And he's, okay, the batteries are flat. Get to get charger on them, or go to get a generator or something like that. So, yeah.
Oh, okay, brilliant. Wonderful. Well, we've come up to an hour, so I'm going to leave it there, but thank you very much, Mike.
Thank you.
I'm just going to quickly pop over to my screen, because I'd love for you all to sign up for the next Technorama Tuesdays webinar, which is happening on the last Tuesday of next month. And it's all on quite relevant that you just mentioned batteries. It's on emergency power, UPS systems, and a few other things. So I've just popped a Zoom link in the chat box. So get ahead of just get ahead of yourself and register for that webinar now. There will be more advertising coming out about it soon. So it would be really great to have you on there. If you want to give us any ideas of what you would like to see in this webinar series, we would be more than happy to have those as well. So please don't be afraid to email the CMTO and let us know, and we'll share it with Technorama. Thank you very much for your time, Mike, and your vast range of knowledge, and for everyone for attending this evening's webinar.
My pleasure. Thank you.
Good night, all.
Night. See ya.
Bye-bye.